What Darwin's theory of natural selection required was time, aeons and aeons of it. This time had been granted to him by the geologist Charles Lyell. His Principles of Geology, published in the early 1830s, laid down the principles of uniformitarianism, the notion that the Earth was slowly built up and broken down, a theory that put forward the idea that the universe was billions of years old, and so too the Earth. But the aeons granted to Darwin by uniformitarian time were about to be taken away from him. William Thomson would later on be ennobled for his work in thermodynamics, becoming Lord Kelvin in 1892. But in 1869, this Presbyterian Northern Irishman made a foray into the debate over the age of the Earth that was going to have drastic repercussions for Darwin's theory of evolution through natural selection. In a paper of geological dynamics read in 1869, Thomson used thermodynamics to argue that the age of the Earth was only 77 million years. And such was his status that Darwin had to listen. If you've ever ridden on a cable car or a chairlift, you've got this man to thank, Fleming Jenkin, and yes, that is how his name is spelt, that is not a typo. Jenkin was an extraordinary engineer and inventor who had been deeply involved in the development of the cable system that allowed messages to be sent around the world during the 1860s and 1870s. Jenkin was an ally of Thomson, and he was no admirer of Darwin's theory of evolution through natural selection. In a review published in 1867 of Darwin's work, Jenkin, then writing anonymously, raised a major problem with Darwin's theory. The problem revolved around Darwin's idea that inheritance was a blend of the characteristics of both parents. Natural selection relied upon the idea of single or small variations that could be beneficial in certain circumstances. Logically, it required these variations to be passed on to subsequent generations. All well and good, except what happens to those single variations when they're blended together with the general population? They just become swamped by the process of blending. How then could beneficial variations be preserved? Faced with the challenge of Jenkin, Darwin developed his theory of pangenesis, which he put forward in his 1868 publication on the domestication of plants and animals. The fact is, in his previous work, he hadn't even really identified an inheritance mechanism, and this was his first attempt to do so. The unit of inheritance, as hypothesized by Darwin, was the gemule. Each parent possessed gemules, a unit of inheritance that carried all the characteristics of the organism that the parents would produce. But those gemules that each parent possessed could be changed during the parent's lifetime. In other words, acquired characteristics could be passed down to subsequent generations. It looks nothing less than some form of Lamarckism. But at least it went some way to countering the critique that Thomson would level against origin. But very few people were happy with pangenesis. Here we see a semi-anonymous critic pointing out some of the serious problems with Darwin's theory of pangenesis. But Darwin at least had his cousin Francis Galton to rely upon. Galton decided that he was going to demonstrate that pangenesis was a viable mechanism of inheritance. If any man were to rescue Darwin, it would be his cousin, an ardent admirer, Francis Galton. Galton was an extraordinary polymath who we will see later on as the founder of eugenics. But anyway, Galton agreed to conduct a series of experiments based on the hypothesis that gemmules were carried in the blood, and he corresponded regularly with Darwin over the period 1869 to 1871. The experiments were carried out on rabbits. Galton would find dissimilar breeds of rabbits, and then he would transfuse the blood between them and examine the features of the offspring. As hard as he worked, he could find no evidence whatsoever of such inheritance. He therefore refuted pangenesis. Now Darwin was undeterred, maintaining that the gemmules must be somewhere else, perhaps at the cellular level, but the fact was few people were going to buy his theory. It's unsurprising then that this period is often referred to as the eclipse of Darwin. And this is where the story always starts, with Gregor Mendel, the monk, and you can see the details of his life listed out there. We can see here the experiments that he did on the pea plants, 29,000 of them, and the publication of his celebrated essay, Experiments in Plant Hybridization. He's always described as the father of genetics. I don't often recommend going to the wiki for its quote, but here I think that it is quite instructive. At first, Mendel's work was rejected, it said, and it was not widely accepted until after he died. He brought forth two generalizations, the law of segregation and the law of independent assortment. Well, what were these laws? The law of segregation maps the inheritance of a trait from two parents and formulates the classic ratio of dominant to recessive genes. And then the law of independent assortment states that different traits are produced independently of each other. And we can see this inherited here with our rough peas and our smooth peas and the dominant and recessive genes, the first generation hybrid, leading to the re-emergence of the recessive genes. Well, that's the story. The fact was that Mendel wasn't aware that he was working in evolutionary theory, that Mendel was widely read, but his theory was read as an engagement with the theory of plant hybridization rather than the evolution of all forms of species. We would have to wait until the 1880s and then the 1890s for a new genetic model to emerge that challenged rather than worked with Darwin's idea of evolution through natural selection. It was in the work of Weismann and de Vries that we find the origin of modern genetics. Weismann, who had been at one time an ardent Darwinian, rejects soft inheritance. He creates a new theory called the germ plasm theory, which elucidates the notion of the Weismann barrier. We can see the operation of the Weismann barrier in this comparison of pangenesis with germ plasm theory. In the case of pangenesis, we have a body with gemmules, the unit of reproduction, and the gemmules are passed on from body to body to body, acquiring characteristics and passing those on to subsequent generations. But in Weismann's theory, the germ plasm gives off the characteristics of the body and gets passed on unchanged from generation to generation. There is a barrier, a one-way street, where the germ plasm cannot be altered by anything that is experienced by the body. Around about the same time, Hugo de Vries, who had also been an ardent follower of Darwin, but had become somewhat disillusioned with the vagaries of pangenesis, moved over to some form of genetic inheritance. And he sees genes and their mutations as the principal means of speciation. What he put forward was the notion that in the underlying genotype, if there was a huge mutation, it would result in a saltation, a leap, a great leap forward, producing a new species. De Vries theorised that the unit of inheritance, Weissmann's germplasm, was called the pangene. Now, in the 1890s, unaware of Mendel's work, he carries out similar experiments and gets similar results. In other words, the discoveries would have been made with or without Mendel. And on the basis of these experiments, he develops laws of genetic inheritance. Now, it just so happened that Karl Krenz had been working in a similar area, but he was pipped to priority by de Vries in discovering the laws. His revenge was to bring up the idea that Mendel had already discovered these laws, and he rebrands what de Vries has done as Mendel's Laws. The reason then that Mendel is regarded as the father of genetics is due to the result of a priority dispute. Without Mendel, the discovery would most definitely have been made. In retrospect, it would seem that it was only a matter of time before the two competing models came together. And I have to emphasize this fact. They were competing models. What we tended to see were groups of people like field naturalists who held on to Darwin's idea of natural selection, often combining it with a vague form of Lamarckism in terms of the way that the environment impacted upon species. Field naturalists remain quite bound to the notion of natural selection. Laboratory workers, however, tended to operate with the new Mendelian model. However, its central concept of speciation through the massive leap forward, the sortation, was beginning to look more and more unlikely. And from about the middle period of the First World War, a number of different mathematicians and biologists started thinking about how genetics might operate with natural selection. And this was the process of the modern synthesis, or the new synthesis, call it what you will, between Mendelianism and Darwinism. The synthesis between Darwinianism and Mendelianism was very much the product of mathematics, or rather the emergence of what we might think of as population genetics. The critical figures in this were two men, Ronald Fisher, author of the genetical theory of natural selection, and J.B.S. Haldane, the upper-class Marxist mathematician who is here proselytizing on behalf of politics rather than Darwinism. Both of these individuals use mathematics to demonstrate that Mendelian sortationism was basically impossible, while at the same time developing models that showed that genetics and natural selection could work hand in hand. In fact, what they're able to achieve is a demonstration of the genetic impact of natural selection on the evolution of species. And then we see other aspects that build upon Darwinism, but take it into new and different zones. If we look, for example, at Saul Wright's adaptive landscape of gene fitness, he establishes a new factor in speciation, the notion of genetic drift operating alongside natural selection. And of course, what genetic drift means is that it's not all down to variation at the level of individual species, some of the species having better adaptations to the environment than others. There might be other factors that operate in terms of selection, including accidents, massive meteorites, those kind of events that no matter how well adapted an individual is, they're not going to survive. So if we were to break down what exactly the modern synthesis was, we can look at the following points. As already indicated, it combines Darwinian natural selection with Mendelian genetics. It demonstrates how natural selection works upon the genotype, despite the fact that there were disagreements over particular factors. There was a general agreement that evolution, speciation, was a result of 5 different factors: mutation, random genetic drift, natural selection, gene flow, in other words, migration or barriers to migration, and non-random mating. Now you'll notice when you look at this list that forms the basis of the movement that we might call neo-Darwinism rather than the synthesis, that only 2 of these different factors were dwelt upon in detail by Darwin: natural selection and non-random mating, which we would call sexual selection. The others were the developments of the geneticists and the mathematicians who had managed to forge this link between 2 fields that had been in desperate competition. To me, this story raises so many different issues about whether we can talk in scientific terms of a Darwinian revolution. What sort of a revolution is it that takes nearly 100 years to play out, on top of which 2 fields come together which at one point weren't directly talking to each other? I must reiterate, however, that this lecture is specifically about whether Darwinism constituted a scientific revolution, and we are leaving out all those other revolutions that might have come on the back of Darwinism that we'll be looking at later in the day. However, in the context of this lecture, what I want you to do is think about a number of things, including the extent to which Darwinism could be constituted a revolution in Kuhnian terms. And if our answer to that is no, then is there another way of conceptualizing it as a revolution? Or do we just see it as the slow accretion of knowledge, tested, falsified, renewed?